Jai Hind. Myself Ravindra Kumar, AP in EN department in AKGEC Engineering College, Ghaziabad. Today I am presenting my topic lecture on the topic steady state analysis of single phase AC circuits in the subject fundamentals of electrical engineering, for which the subject code is BEE 101, and this topic is covered under second unit, that is steady state analysis of single phase AC circuit. This is the unit name, and in this we will take different things like the generation of sinusoidal AC wave, advantages of AC over DC, and why the AC wave is sinusoidal wave, various terms related to AC wave, the definitions of those terms, plus how to find RMS value, average value of sinusoidal AC wave and other types similar waveforms. For those we are to find, and then to find form factor and peak factor from that. All those things we will cover under this topic. So, if we see it, these are the contents in this. One is we are how to repaint the sinusoidal waveform, then advantages of AC over DC, why AC is in sinusoidal form, what is the reason for this, that will be covered. How to generate sinusoidal AC, the method applied for this generation of sinusoidal AC, then the definitions of various terms in AC, how to calculate average and RMS value, and then the form factor and peak factor. So, all those topics will be covered under this lecture or under this discussion. So, if we say it, first thing is basics of AC, that is alternating current. So, if we see the definition of this, a sinusoidal AC waveform that starts at 0, then increases to a positive value, maximum value, positive maximum, then decreases to 0, changes its polarity, increases to a negative maximum, and then returns back to 0. That way it completes a cycle. So, this variation, all these variations, that is known as a cycle or complete cycle. And the AC sources, they have sinusoidal waveform. So, this is shown in this diagram, waveform diagram. If we see it, here it is starting from this 0 point, this point is 0, then it is increasing to this positive maximum value, this is the maximum value here and in positive direction, then again it is decreasing to 0 value, it is again 0 here, then it is going to the negative side and reaching to the negative maximum at this point, then finally coming back to 0 again. So, that way from this which point it is started, at the same point it is completed or finished. So, that way it is a complete cycle. So, it is we are having voltage waveform. On the x axis we can take time or angle theta, that may be there, and on y axis we can take voltage or current V or I, anything it may be there. Here we are repainting it voltage wave, it may be current wave also. So, at this point this is the crossover point, 0 crossover point we call it, polarity changes from positive to negative. In this half cycle it is positive polarity, and in this half cycle it is negative polarity, and from this point 0 up to this point 0 again it is a complete cycle. So, we can say it is a complete cycle, and in this there are two half cycles included. First one is positive half cycle, in which the variations in the voltage is in positive direction, and second one is the negative half cycle, in which the variations are in negative direction. So, that way it is represented, and this is known as sinusoidal AC waveform. Why we call it sinusoidal? Since it is similar to the sinusoidal waveform, that is why it is sinusoidal AC voltage or current waveform. Further, if we say advantages of AC over DC, since we can supply electricity with the help of AC waveform, or we can have it in DC form also. So, there are certain advantages if we take AC in comparison to DC. What are those advantages? We can say it, AC can be transmitted using step up transformers, but in DC it cannot be done. Reason being, transformer works on the principle of mutual induction, and mutual induction takes place in AC, it cannot be there in DC. That is why voltage step up or step down, or we can say change in the voltage level with the help of transformer, That is possible in AC, not in DC. So, that is why AC can be transmitted by using a step up transformer to the long distances, which is not possible in case of DC. Next reason, AC is easy to generate than DC. That is also the reason for this. That is why we prefer AC. Next reason, it is cheaper to generate AC than DC. That is also the advantage of AC over DC. Another reason, the loss of energy during AC transmission is less in comparison to DC. The reason for this is, when we are transmitting electricity or electrical power to the long distances, that time we take it over higher voltages, and higher voltages that are possible with the help of step up transformer in AC, not in DC. And using these higher voltages, the current in the line that reduces, and due to the reduction in current in the line, transmission line, I square R losses, which are also known as heat loss, they are reduced, and with the reduction of those losses, the efficiency of the system that improves. That is why the system becomes more efficient due to reduction of losses, I square R losses basically in AC transmission. So, these are certain advantages of AC over DC. That is why we prefer power transmission with the help of AC rather than DC. Now, another topic, why the AC which we are generating, that is sinusoidal. What is the reason? Otherwise, it may be in other form, like it may be triangular AC, it may be square AC or trapezoid form AC, but why we prefer AC in sinusoidal form? That is also one of the question mark we can say. So, if we see the answer of it, the reasons for this is, sinusoidal form is easy to generate as compared to square waveform or ramp signals. That means, when we are generating AC in sinusoidal form, it is easy to generate in comparison to if we are generating square AC or ramp type of signal in AC waveform. So, that is one of the reason. Another reason, sinusoidal form is easy to analyze mathematically. That means to say, all the calculus tools work wonderfully for the curves like sine curve or cosine curve. Calculus tools means here differentiation and integration, they are the calculus tools. So, they work easily in case of sinusoidal or cosinusoidal form rather than any other type of form, like if we take square waveform or ramp waveform, that means triangular waveform type waveform. So, that time the integration and differentiation of those waveforms, they are more complex in comparison to sinusoidal or cosinusoidal waveform integration and differentiation. Since simply there are the formulae with the help of which we can differentiate and integrate a sine curve or cosine curve easily. So, that is why these calculus tools, they work easily or wonderfully for the curves like sine curve and cosine curve. Other than that, calculus tools tend to be more inconvenient for other types like square or ramp waveform. That is also the problem. That means to say, if we are using these calculus tools for square or ramp waveform, that become more complex or inconvenient, in other words we can say. So, that is why we prefer AC in sinusoidal waveform. Now, other thing, how to generate AC, that is the important thing, that what method we should apply to generate AC. Basically, there are two methods for generation of AC. One is, what can we do? We are rotating a coil in the uniform magnetic field at uniform angular velocity. By doing so, we can generate AC. Second method is, we are keeping the coil stationary, but the magnetic field in which the coil is placed, that magnetic field is time varying magnetic field, but the coil is stationary in the time varying magnetic field. So, that time also it is possible to generate AC with the help of that method. So, basically these are the two different methods for generation of AC. One is to rotate a coil at uniform angular velocity in uniform magnetic field, and second one is to keep the coil stationary but in a time varying magnetic field. So, we are in this example or in this method, we are taking the first method. We are rotating this coil. This is a coil, rectangular coil, which it is shown in this diagram. We are rotating this coil in the uniform magnetic field at uniform angular velocity. And these are the two terminals of this coil. One is this terminal, another one is this terminal. At these two terminals, slip rings are connected. This is the slip ring, it is shown in the diagram. Similarly, this is the slip ring. They are connected at these two terminals of these two coils, and in between these slip rings, we can connect some resistance through which current can be passed. So, that way the circuit is completed for this coil. This resistance, we can say this is external load resistance. So, basically this is AC generator. Now, here we can see other things, this north pole and south pole, and for north pole as for south pole. So, these are the two poles of a magnet. These may be permanent magnetic poles or these may be electromagnetic poles, that depends. If it is a small generator, that time they may be taken permanent magnet pole. If it is a large size generator, that time these poles may be electromagnetically generated poles. Anything can be there depending upon availability and requirement. So, we are rotating this coil in this magnetic field of this magnet. Now, we know the direction of magnetic field outside the magnet is from north to south. So, this will be the direction of magnetic field, north to south, outside the magnet, and inside the magnet it is south to north. So, if we want to complete this magnetic field line path, so inside the magnet it will be like south to north, this way, it will complete its path. So, this is the magnetic field line path. So, now in this, when we are rotating this coil in this magnetic field, what will happen? The flux linking with this coil, that will change continuously with time, and due to the change in flux with time continuously, an EMF will get induced in the coil as per Faraday's laws of electromagnetic induction, and that will be given by E equal to minus n d phi by dt, where this small e, that is the induced EMF in this coil, n is the number of turns in this coil, d phi by dt represents rate of change of flux linking with the coil with respect to time, and this minus sign it is representing due to Lenz's law, that this induced EMF in this coil that opposes the change in flux linking with the coil. So, if we see it in detail in the next slide, we can see it, that how the AC is generated with the help of this method. So, if we see it, these are the various positions of the coil when we are rotating this coil in the magnetic field. From these different locations, we can see we are rotating this coil in clockwise orientation like this. That is very much clear from this diagram. We are rotating this coil, rectangular coil, in the magnetic field of the magnet in clockwise orientation. So, if we see in this first diagram, diagram B, that means magnetic field, that will be, it is suppose north pole and south pole. So, that this is north pole and south pole. So, magnetic field will be like this, and similarly here it is the magnetic field orientation. So, in diagram B, the coil is facing this magnetic field and coil is having its surface perpendicular to the magnetic field, that we can see in this diagram, that coil surface is perpendicular to the magnetic field. So, the maximum flux phi max, that will be linking with the coil in this case, that will be given by B into A, where B is the flux density of the magnetic field and A is the area of this coil, surface area of the coil, which is perpendicular to the magnetic field. Now, after this rotation of this coil, when coil comes to this position, that time the area of this coil, that is parallel to the magnetic field. So, the flux linking in this case will be 0. Now, after further rotation in the clockwise direction, we are rotating the coil. Now, again this face of the coil that is perpendicular to the magnetic field. So, the again maximum flux will be linking with the coil, but that will be negative now, reason being opposite face of the coil that is perpendicular to the magnetic field in this diagram D in this location. So, this will be minus B into A, that means. Now, further rotation after this, if we see here, what will happen? Again the face of the coil that is parallel to the magnetic field, that we can see in this diagram. So, the flux linking will be 0 again here. And now, in this diagram F, if we see, again this face is perpendicular to the magnetic field. This case is similar to the first case, which is diagram B and diagram F. They are exactly similar. So, again there will be the maximum flux linking with the coil, which will be B into A. So, that means with the help of the different diagrams or different coil locations due to the rotation of the coil at a uniform angular velocity in the uniform magnetic field, we can see the flux linking with the coil is continuously varying with time, and due to this varying flux, time varying flux linking with the coil, an EMF gets induced in the coil, which is already we have seen given by E equal to minus N d phi by dt, that we have seen here as per Faraday's laws of electromagnetic induction. So, what can we see here? If we take phi equal to the expression of flux, phi equal to, we can take phi max cos omega t. Since at t equal to 0, this is we take at instant t equal to 0. This is instant t equal to pi by 2. This is t equal to pi. This is t equal to 3 pi by 2. And this is t equal to 2 pi. So, at t equal to 0, since the maximum flux is linking, so if we see from this expression phi equal to phi max cos omega t, cos 0 is 1, we know. So, that is why phi will become phi max this time. At t equal to pi by 2, this cos pi by 2 is 0. So, flux will become 0, that is this. At t equal to pi, so cos pi is minus 1, that is why flux will be maximum but negative, that is this. At t equal to 3 pi by 2, so we know cos 3 pi by 2 is 0. So, that is why flux will become 0 in this case. And finally, when t equal to 2 pi, so that time the flux will become again maximum, since cos 2 pi is 1. So, this is phi max, maximum flux in this case. So, that way this flux is varying from maximum to 0, then 0 to maximum again, but in negative direction, then again negative maximum to 0 and 0 to positive maximum again. So, that way this flux is continuously varying with time. So, if we find this induced EMF, so that will be given by minus N d phi by dt, that already we have seen in the last slide why it is so. So, this will be minus N into differentiation of flux, which is phi max cos omega t with respect to time t. So, this E will come out as minus N into phi max. Now, the differentiation of cos omega t with respect to t is minus omega sin omega t. So, this is equal to omega n phi max sin omega t. So, this is the expression of induced EMF, and this omega n phi max, this is known as maximum value of induced EMF. So, this is E max sin omega t, we can write small e equal to E max sin omega t. Small e is known as instantaneous value of induced EMF, this small e. E max is the maximum value of induced EMF, omega is angular velocity or angular frequency, and t is time in second. Omega is given by 2 pi upon t, where capital T represents time period, and that is the time required for completing a cycle. So, f is equal to 1 upon t, that is the frequency. So, if we see the generation of AC, that is shown also in this diagram, At t equal to 0, this is the position at this point. E will be 0. As per this equation, we can see E equal to E max sin omega t, that we have found. E equal to E max sin omega t. So at t equal to 0, it will be 0 at this point, we can see. At t equal to pi by 2, so sin pi by 2 is 1. So maximum value of induced EMF will be there. So that is this point at t equal to pi by 2. This is pi by 2. At t equal to pi, sin pi is again 0. So at t equal to pi, this is 0 at this point pi. This is point pi, it is 0. At t equal to 3 pi by 2, if we see sin 3 pi by 2 is minus 1. So this is coming here at negative maximum corresponding to this. So this is 3 pi by 2. And at t equal to 2 pi, if we see, so sin 2 pi is 0. So that's why it is completing its cycle and coming here at t equal to 2 pi, this point. So that way it is a complete cycle of this waveform which is generated. How it is generated, that is explained in this. From t equal to 0 up to t equal to 2 pi, this is a complete cycle of this waveform. It is t equal to 0 here, and this is t equal to 2 pi. This is t equal to 0 and this is t equal to 2 pi. So that way this generation of AC is there, and the method is we are rotating a coil at uniform angular velocity in a uniform magnetic field. Further, if we see, so finally we get such type of waveform. This is AC which is generated. This is instant t equal to 0. This is instant t equal to t by 4 at this instant. And this is corresponding to this. We are taking current waveform here. So this is maximum current. If it is voltage waveform, then it will be maximum voltage. This is instant t equal to t by 2. Here the current is 0 or voltage is also 0. At this instant t equal to 3t by 4, the current is negative maximum, or if it is voltage waveform, then voltage will be negative maximum. And finally, when the cycle is completed at this instant t equal to capital T, since capital T is time period, so the value of voltage or current will become 0. So if we take it in terms of angle, so this is instant 0 or angle is also 0 degree. At this instant when t equal to t by 4, angle is pi by 2. At t equal to t by 2, angle is pi here at this point. Here it is angle 3 pi by 2 and it is 2 pi. So that means capital T represents 2 pi, which is a complete cycle of the waveform. So this is the complete cycle of this waveform, and this is we call sinusoidal waveform, since it is having sinusoidal variation in the itself. That's why it is sinusoidal AC waveform. So this type of waveform is generated with this method which we have explained in the previous slide to generate AC. Now if we see the different terms, definitions related to this AC, what are those terms that we can see? AC voltage or alternating voltage and current vary continuously in magnitude and reverse in polarity. That we have seen in the previous slide, that they also reverse in polarity, and the magnitude of these voltage or current, AC voltage and current, they change continuously, that we have seen here. One complete set of values in one cycle of the AC waveform, that is there, that we have seen, and one cycle includes 360 degree angular measurement or 2 pi radian in radian measurement, that we have seen here also, that it is 2 pi complete cycle, 2 pi radian or 360 degree. 2 pi radian, that means 260 degree. Other than that, if we see other terms, instantaneous value, that means it is the value of the waveform at any particular instant of time, or the magnitude of a waveform at any particular instant of time, and this is denoted by the symbol small e or small I. So, small e represents instantaneous value of the EMF which generated, and small I represents instantaneous value of the current generated, that we can see in this. This small I is instantaneous value, that is the value at any particular instant of time. Or if we take small v, we can also take small v. So, that will become instantaneous value of voltage, that means the value of voltage at any particular instant of time. So, this is instantaneous value. Then we have peak value, the maximum value, that is also known as peak value. So, this we also can say maximum instantaneous value of a function as measured from 0 volt level or 0 current level, that is known as peak value. The other name of this peak value, maximum value, peak value or maximum value, I write it here, peak or maximum or crest value, that is also the name of this, crest value, CREST, crest value, or amplitude. These are the different names. Associated with it. Then the next term is period, that is time period basically. So, this is the time interval between successive repetitions of a periodic waveform. So, when we are taking successive repetition of a periodic waveform, so the time interval between those, that is known as time period. Like we have seen here, from this point 0 up to this point, this is a successive repetition. So, the time interval between this, that is capital T or 2 pi, that is time period. Then the cycle, that is a portion of a waveform contained in one period of time, that is known as cycle. Like we have seen this, from this point up to this point, this is a complete cycle, that is there. Then frequency, frequency means the number of cycles per second or that occur in 1 second, that we call frequency. That is why frequency is reciprocal of time period. Since time period means the time taken for completing one cycle, and frequency means the number of cycles that can occur in 1 second, that is frequency. So, that way the different terms definitions are there. Next we have what is average value and RMS value of this sinusoidal AC waveform. So, first we go for average value. Average value is also known as mean value or average value. So, if we find it, the mean value or average value of a sine wave, we write it E mean as integration of instantaneous value over half cycle, that is 0 to pi, divided by the duration of half cycle. We can also find it for a complete cycle, but for a complete cycle this average value will become 0, and the reason for that is the areas covered under positive and negative half cycle. That means this area covered under positive half cycle and negative half cycle, these areas are equal in magnitude, but of opposite sign. That is why the total area covered under one complete cycle of this AC sinusoidal AC waveform will be 0, and that will give us 0 average value or mean value if we want to find it over a complete cycle. So, that is why in this case we find it for half a cycle, and this waveform is also known as symmetrical waveform. Reason being the positive half cycle area, this area, and negative half cycle area, this area, they are exactly the equal magnitude areas and with the opposite signs. So, that is such type of waveform, they are known as symmetrical waveform. So, we were talking about this average value. So, now what we do, we find integration of this instantaneous value over half cycle. That means we are adding all the instantaneous values which are occurring in half cycle and then dividing it by the duration of half cycle. So, that will give us the mean value or average value over half cycle. So, in place of small e, we can write the expression E max sin theta. So, we integrate it now with respect to theta in the half cycle duration 0 to pi and divided by half cycle, that is pi. So, the differentiation of sin theta with respect to theta is minus cos theta, and the time limit, the limit for theta is 0 to pi. So, if we solve it, it comes out as 2 E max by pi. Since cos pi is minus 1 and cos 0 is 1. So, on putting those values, it is simplified by 2 Emax by pi, and that is 0.636 into Emax. So, this is the average value of sinusoidal AC waveform over half cycle. So, now, this is the symbol E mean means mean voltage value and E max means maximum voltage value. Similarly, if we take it for current, so that time mean current value will be 0.636 into maximum current value, where I mean represents mean current value and I max represents maximum current value. Similarly, we can find RMS value. So, if we see it, first the definition of RMS value. RMS value is also known as effective value, and the full name of RMS means root mean square. R for root, ROOT root mean square. So, RMS value means root mean square value, also known as effective value. So, if it is defined as effective value of AC is an equivalent DC value which tells how many volts or amperes of DC that a time varying sinusoidal waveform is equal to in terms of its ability to produce the same power. That way we define effective value or RMS value. Now, if we want to find it mathematically or analytically for a sine wave, how do we do it? Root mean square value. So, we start from right side. First we take square. So, what we do? We take the square of instantaneous value, that is E square. Then mean, we take the mean over a complete cycle. So, for that what we do? We can add or we will add all the E square terms which will take place in a complete cycle, and for that we integrate E square with respect to theta in the complete cycle range, that is 0 to 2 pi, and then divide it by the duration of complete cycle, that is 2 pi, and finally we take the root. First we have taken square, then mean of that square, and then we take the root of all this. So, this is the root. So, that way we find RMS value. So, now if we simplify it, first we put the value of small e here. So, this is E max sin theta, square of that becomes this. We integrate it now with respect to theta in the limit 0 to 2 pi. So, this is E max square, that will be outside the integration since it is independent from theta, and sin square theta can be written 1 minus cos 2 theta by 2. This is this, and then we integrate it with respect to theta. So, this comes out as this, and limit is applied 0 to 2 pi. So, after applying the limits, sin 2, when we apply upper limit in sin 2 theta, so this becomes sin 4 pi, which is 0, and when we apply lower limit, so that time sin 0, that is also 0. So, that means this part sin 2 theta by 2, that becomes 0 for both upper limit and lower limit. Only the limits will give the result for theta only. So, that is why the final result comes out as this, E max by root 2 or 0.707 into E max. So, this is the RMS value of sinusoidal AC waveform with the help of this analysis. Similarly, if we want to find it for a current waveform, so that time the RMS value of current waveform will be 0.707 into the maximum value of current for the given waveform. So, this is the method for this. Now, further with the help of it, we find form factor and peak factor. Form factor, this is also written in short FF. This is the ratio of RMS value to the average value, and by putting the RMS value and average value here, which we have found earlier. So, this is coming as 1.11, and this is represented by symbol KF. So, KF comes out as 1.11 for sinusoidal AC waveform. Similarly, another factor, that is peak factor. It is represented in small abbreviated form or short PF, peak factor. This is the ratio of peak value to RMS value, and by putting the peak value and RMS value in this, we find peak factor as 1.414 for sinusoidal AC waveform, and the symbol for peak factor is Kp. So, that way we calculate peak factor and form factor for a sinusoidal AC waveform. If we see some more example for this, similar type of sinusoidal waveform we can take other waveform, like we have half wave rectified waveform. So, what we do, by having single diode we get half wave rectified waveform when we are using single diode in a circuit. So, this is the complete sinusoidal AC waveform, this one. This we give input to the circuit which is having single diode, and diode gives this type of output. This is half wave rectified AC waveform. Why we call it rectified? Since it is only in one direction, not in both the directions. Now, here if we see the cycle of this waveform, it is from 0 to 2 pi. Since at 2 pi it is repeating itself in the same manner as it was on 0. At 0 the magnitude is 0, at 2 pi also the magnitude is 0, at 0 it is going in this direction, at 2 pi also it is going in this direction. So, that is why the complete cycle is from 0 to 2 pi. So, if we find the mean value and RMS value for this half wave rectified waveform, so that will be for complete cycle we will find, since it is not a symmetrical AC waveform. So, mean value will be integration of instantaneous value over complete cycle 0 to 2 pi and divided by the duration of complete cycle, that is 2 pi. And then now we put the value of small e, that is E max sin theta, since the equation will be small e equal to E max sin theta, and theta is known as equal to omega t, that already we have taken here also in the very first here, E equal to E max sin omega t, where omega t equal to theta. So, that is why we can write E equal to E max sin theta also. Yes. So, this is E max sin theta. Now, we integrate it with respect to theta in the time limit of theta 0 to pi we are taking and divide by 2 pi. Why we are doing so like this now? See, this limit 0 to 2 pi, this is broken in the two limits, one is 0 to pi and then other limit is pi to 2 pi. Now, this E equal to E max sin theta, this is for theta equal to 0 to pi, that we can see here in this waveform, this is this one, and E equal to 0 when theta is between pi to 2 pi. That also we can see here, this is pi to 2 pi duration, in this duration E is equal to 0. So, when this limit is broken from 0 to pi and pi to 2 pi, so 0 to pi will give this result and pi to 2 pi integration will become 0, since in pi to 2 pi small e is 0. So, and divide by 2 pi. So, after solving it we get it equal to E max upon pi after solving this integration. Similarly, if we find RMS value, so that will be under root of integration of E square with respect to theta in the limit 0 to 2 pi and divided by 2 pi. Again we will break this limit into 0 to pi and pi to 2 pi. In the 0 to pi we will get integration, that is this 0 to pi integration E max square sin square theta with respect to theta integration, and in limit pi to 2 pi this integration will become 0 again, since E is 0 in the limit pi to 2 pi, and divide by 2 pi and root of this, finally we get this result E max by 2. So, this is the RMS value which is max value by 2 and mean value, that is max value upon pi for half wave rectified wave, and with the help of it we can also find form factor and peak factor for this waveform if it is required to find. That can also be found with the help of definition of form factor and peak factor, or the formulae which are used for finding form factor and peak factor for a given waveform. Similarly, another example, if we take full wave rectified wave, that is for this is the input waveform, sinusoidal AC waveform. When we pass through a circuit which is having double diode, two diodes, that means then we get output of that circuit which is having two diodes in this form, that is this output. Here it is 0, then this is pi, 2 pi, 3 pi, 4 pi and so on, and it is here 0, pi, 2 pi, 3 pi, 4 pi and so on. So, this is full wave rectified waveform, and for this the complete cycle is from 0 to pi, since it is repeating itself for 0 to pi, that means at pi instant it is repeating itself. Since at 0 it is 0 magnitude, at pi also it is 0 magnitude, at 0 it is going like this, at pi also it is going like this. So, that is why a cycle is from 0 to pi for this waveform. So, we can find mean value or average value and RMS value, which is also known as effective value for this waveform, but for that we are to find it for a complete cycle which is 0 to pi, and we will write the waveform expression as E equal to E max sin theta, where theta is varying from 0 to pi. So, the mean value or average value, that will be integration of instantaneous value over the limit 0 to pi with respect to theta divided by the duration of complete cycle, that is pi. So, by putting the small value of small e, which is E max sin theta, in this integration, and by solving this integration we get 2 E max by pi. This is the mean value or average value of this full wave rectified wave. Similarly, RMS value, that is under root of integration of E square with respect to theta in the limit 0 to pi, which is the complete cycle, and divided by the duration of complete cycle, that is pi. So, now we put the value of small e, which is E max sin theta, in this integration, and then we solve this integration, and finally we get this result E max by root 2. So, that is the RMS value of this fully wave rectified waveform. So, once we find this RMS value and average value of this waveform, then after we can find form factor and peak factor also for this full wave rectified waveform. So, that way we can find form factor, peak factor once we get the values of RMS value, that means, and average value we can find from that for any type of given AC waveform. Like in this case we have seen it, or we have found it for sinusoidal AC waveform, half wave rectified waveform, and full wave rectified waveform. So, that is all about this. In the next lecture we will be taking the next topic related to the AC waveform. Thank you.